the heart of this course was really statistical inference, and it's either about trying to understand the data that we've collected in order for us to make decisions about what is happening, or it's about trying to estimate parameters of a population so that we can use that in probabilistic models to make predictions in the future. And so one of the cores of what we're doing here in statistical inference is this parameter estimation, and two large important ways that we've gone about doing that is to look at point estimates and to look at intervals. And so in the point estimate approach, we had two basic ideas: the method of moments, the maximum likelihood approach, where in the method of moments our estimator for the mean was our sample mean, and our estimate for the method of moments for the variance was the sample variance that was defined with not the 1 over n minus 1, but the 1 over n. And unfortunately, this was a biased estimator, which meant that the expected value of this was not exactly equal to the variance, and instead, to get an unbiased one, remember we had to use the sample variance that was defined with the 1 over n minus 1 approach. And then the other approach is to use the maximum likelihood approach to develop a point estimate kind of approach. For the purposes of what we do, we tend to, in the statistical world, when we're working with things that are not new, well, then we already know what our estimators are, and it's more of just processing the data and interpreting the results of that. Right. And then for pairs of data, then we have a variety of sample calculations that we could make. One of them is this mix that led to covariance, and so there's the approach of taking the deviation away from the mean of one variable, and then you got this pair, so the deviation away from the mean from the other one. When we do it in this case with 1 over n, that's biased. If we use n over n minus 2, and I'm going to rewrite this in a slightly different format here, the mean of the product of x times y minus the mean of x times the mean of y. That'd be the sample ones, and this is an unbiased version, right? So, you know, if you go back up to this previous expression, we have xi times yi, and we sum up all of those and divide by n. That's the sample mean of all of those, right? So that's really what this represents, a big sum. This represents the sum of x bar all by itself, and this one is the sum where we calculate y bar all by itself. And then the sample correlation coefficient, Rxy, is equal to capital S xy over the sample standard deviation and sample of each one, x and y. Right, now when it comes to intervals, remember that the basic overall format for these confidence intervals was the idea that if, let's say it's two-sided, that we have some estimator from the sample data, and then plus or minus some multiple that was associated with, say, sub alpha, and then we'll have some sort of estimate of the spread or the standard error, depending on what it is that we're working with. Right, so standard error, that's the spread associated with our estimator, and then K alpha was the associated with the confidence level and the distribution that's at work here. Right? So rather than be too concerned here at the moment about, wait a minute, what was this again? How do we find each of those? Big thing here, we start with some estimate of the out of the sample data, sort of our sample mean, so to speak, if we're going with a true mean, plus or minus, then some multiple of a standard deviation is what this all amounts to be. And everything is just a variation, really, on that theme. So, for instance, a confidence interval for the true mean, and remember, another aspect of this is that the underlying distribution is normal. In under a variety of situations we can relax that, but that's where we started off with most of this work. And so for the mean, when our underlying population variance was known, then we looked at z being equal to x bar minus the mean divided by our population standard deviation square root of n. And remember that this is really the mean of the coming from the sampling distribution, right? And so, but mean of x bar, remember that sample mean, the expected value of x bar, is the mean of the population itself. The variance of that, though, was equal, of x bar was equal to sigma x over the square root of n. So that's how this differed from, say, just a regular normal distribution population. Right? And it was along with this that we could also look at establishing a sample size that would go along with some particular, say, two-sided confidence interval that we were interested, that z value, knowing sigma, knowing the error that we were interested in, we could come up then for those given values of sigma e and come up with a sample size for our testing, sort of a design of an experiment if we wanted to. Now, when sigma x is not known, then we substituted in with what we found from the sample. And so that would be just the substituting in the sample standard deviation, and that became the t-distribution with n minus 1 degrees of freedom. Right? And so once we had set what the confidence level, significance level was, so to speak, the confidence level that we wanted, that gave us the alpha. And if it was one-sided or two-sided, that gave us this right here. If it was sigma x known, then this becomes z alpha over 2 for two-sided. If it was sigma x unknown, and we had less than 20 in our total sample size, then it was t-distribution, and so this became a t alpha over 2, right, for two-sided. And so that's what goes into that, and then whatever if this is our sigma x known, this becomes then associated with our standard error here, bam, this guy, and otherwise it becomes this one with the t-distribution. Right, now for variance, on the other hand, then that led to the examination of n minus 1 times our sample variance divided by our population variance was then chi-squared distributed with n minus 1 degrees of freedom. And it was from that we developed the confidence interval in a similar kind of way. Right. For proportions, then we looked at that we were going to use a normal approximation for a binomial variable, and that led us to that the equivalent of one of these guys here, and now it becomes a z, was x minus np over square root of np 1 minus p. So once again we end up with that this is somehow a mean, and this is somehow the standard deviation associated with our test statistic. Well, it's not really a test statistic like hypothesis test, but it's our statistic that we're taking a look at. And this approximation that we end up with, we're going to divide through by n, and when we do that, well, x over the n is our proportion that comes from our sample minus our true proportion over the square root of then p hat 1 minus p hat over n. Now, really, you only have p in here, but we need to estimate that. We don't know what that is, so we're going to estimate it from our sample and then develop our confidence interval associated with that. And that's your z. That's that normal approximation that we're working with. Right now, for prediction intervals for the next observation, this is not a confidence interval anymore, this is a prediction interval. For based upon a sample, come up with a prediction of the next one, next observation that we're going to have. And in that case, that's x bar, our sample mean from what we just collected, plus or minus, and then t alpha or 2, assuming that we have an unknown standard deviation, and then that'll be square root of 1 plus 1 over n. And then for the tolerance interval, that's really just x bar plus or minus a tolerance constant times our sample standard deviation, where we get that k out of tables, but it's really very much associated with the t-distribution again, just as before.